All right, good morning everybody and welcome to the July NWA Webinar Wednesday. My name is Tricia Palmer and I'm co-chair of the NWA Professional Development Committee. Today's webinar is titled Hello World, I'm GOES-16 and I'm here to help. We actually have three presenters today, each with their own sub-presentation. We have Frank Alsheimer, Brian Motta, and Sheldon Kusselson. Frank is the chairman of the NWA Remote Sensing Committee and he's the Science and Operations Officer with the National Weather Service Forecast Office in Columbia, South Carolina. His presentation is the GOES-16 Advanced Baseline Imager has arrived. Brian is currently a meteorologist instructor with the National Weather Service Headquarters Office of the Chief Learning Officer in Boulder, Colorado. He's been involved in GOES-R science team meetings and GOES-R User Readiness activities for the last 15 years, and he will be presenting on the GOES-16 Geostationary Lightning Mapper. Sheldon is a retired operational meteorologist who worked for 36 years for NOAA's satellite service, and he now provides satellite imagery and product applications information to NWA broadcasters. And he'll be presenting on integrating blended polar orbiting microwave products to help enhance your GOES-16 imagery product experience. Before we get started, just a quick reminder that if you have any questions, you are free to ask them via the GoToWebinar software, or you can ask via Twitter using the hashtag NWAWebWed. That's hashtag NWAWEBWED. John Bangoff, our student member of the Professional Development Committee from Penn State, will be helping to monitor Twitter for me. Rather than saving all the questions for the end, we'll take a couple of minutes after each presentation to address any questions pertaining to that particular topic. And speaking of Twitter, I also want to thank Elise Hagner with the NWA Social Media Committee for helping out with some live tweeting this morning. Again, thank you all for joining us today, and I will go ahead and pass this on over to Frank.
Good morning, everybody, and this is one of the rare times where I can say still good morning to everybody. Usually there's some time differences going on, but I want to welcome you to our presentation this Wednesday. I hope you find some interesting information. We're obviously just scratching the surface of this brand new instrument that's got all kinds of possibilities going forward. I'm going to talk about specifically the Advanced Baseline Imager, which is probably the most information that you've seen lately with, anybody who follows weather. Twitter, for instance, has seen all kinds of posts on these great images that we're getting. So we're going to talk a little bit about the instrument, some of the background, and then give you a little sample of what some of the potential products that we have coming forward. It's not just the images, but we have a lot of products. So here I am. And thanks to a whole lot of people, and I'm sure I probably missed some additional people along the way, but this is the whole GOES-16/S program has been a long time coming, and the amount of effort that's been put into it to get it up in the air and getting information out to everybody has been really a monumental task, and a lot of people have been involved with this. So again, I don't have everybody on there, but I think maybe the entire GOES-R team is most equivalent for that. So briefly, in my time here this morning, I'm going to talk about the GOES-16 or S ABI, which is the Advanced Baseline Imager, and that's the one we're getting all the nice images from now. And I'm also going to briefly talk a little bit about Derived products and the fact that we still have work ahead of us to get things done. So let's take a really nice image there of the Advanced Baseline Imager. This is courtesy of Lockheed Martin. And compared to what we've had in the past, we have a significant improvement in our spectral, our spatial, our temporal, and also something that may not go noticed, but is very important, is there's also been a significant improvement in the way we calibrate the information. So let's look into a little bit of the details for how these have improved over the previous GOES series. You notice the table here, I've got current imager, that's really like GOES-13, GOES-15, and the ABI is from GOES-16 and GOES-S, which will eventually go to GOES-West, which is, by the way, currently scheduled to be launched in March of next year. So we've gone from 5 bands on the current GOES to 16 bands on our GOES-16, a threefold increase The spatial resolution increase has really been noticeable, especially if you've been looking at some of the visible loops from some of the sites that have that information available. The detail is pretty tremendous. We've gone from about 1 kilometer to half a kilometer. We've also got several other bands, and we'll get into the different bands in a moment, that are 1 kilometer now that we simply didn't have before. And then we've got an awful lot of these IR bands that were in the past 4 kilometers and are now 2 kilometers. Of course, the spatial coverage has significantly increased. Right now with the current imagers, there's scheduled 3 hours between full disk shots. Now we're getting at least 4 per hour, and we could get as many as 12 per hour depending on the scan strategy. We have image that covers the CONUS 12 per hour, essentially every 5 minutes, whereas in standard operation of the GOES-13 and 15 satellites, you would get 1 every 15 minutes, so about 4 per hour. And then something we didn't have on the previous imager is that we have these 2 mesoscale sectors where we can get 30-second imagery if they're on top of each other, or 1-minute imagery if we have 2 separate mesoscale sectors running at a given time. We'll talk a little bit more about the mesoscale sectors in a minute. So here's kind of a spatial view of what we're talking about in terms of our improvement. We've got 5 times faster full disk coverage, at least. We've got 4 times the improved spatial resolution at pretty much every band. And we've got 3 times an increase in the spectral. We've gone from the 5 bands to the 16 bands. So let's briefly take a look at these different bands here. Well, let me first show you a picture of what the typical mode. We're probably going to be mostly in the scan mode 3, which is called flex mode, and that'll give us the 15-minute full disk imagery, the 5-minute CONUS sector imagery, and then the 2 1-minute mesoscale sector imagery. And you can see in this image here the relative, right now of course it's at 89.5, which is its checkout position, but in November it will be moving over to 75, which is its east position. You get an idea that there is obviously, as you get further away from nadir, there's a little parallax so that the resolution is not exactly the same as you move north and then east and west. But you'll get all that every 15 minutes, then 5 minutes you see an approximate outline of the CONUS sector, and then of course every minute, or if you have them on top of each other, you can get 30-second imagery in these roughly 1,000 by 1,000 kilometer squares. Now there is what we call a continuous full disk mode, which is scan 4, and instead of this being 15 minutes, it would be every 5 minutes. There have been a few tests on that. There may be some occasions where that's used, but I think in general for operations, it'll probably be more often in flex mode than it will be in continuous full disk. So here's kind of how the mesoscale sectors are sort of set up to work. You'll see 4 of them on there right now. That is the final layout once we have GOES West also flying. Right now, since we have the GOES in the test position, GOES-16, and it will go east, the main 2 mesoscale sectors, we'll call them the default ones, are set up as shown here, the 2 on the right. Now, the reason why those were picked is because those cover our main aviation corridors. You see, we got a lot of the really heavily trafficked airports in the eastern half of the country covered by these 2 mesosectors. You've got the Chicago area, the Atlanta area, Charlotte, St. Louis, and of course the very busy Northeast corridor. Now what will happen with these mesoscale sectors is that somebody may make a request to cover, say, severe weather. SPC has been doing this quite a bit to cover their slight and especially their enhanced risk areas. And during those times, these mesosectors will move so that they're centered on the area of interest for the time period of concern. When there are no specific requests to have those mesoscale sectors in a specific place, they will default back to those 2 locations. Of course, once we get GOES-S up, it's gone through its testing and it's moved to GOES West, then we will have 2 additional corridors Again, the default position will be trying to look at some of those heavy aviation corridors, such as the Dallas-Fort Worth area up to Chicago and California, out through Las Vegas area and so on. But again, those will also be able to be requested and moved under the same circumstances. So let's look at the individual bands now. Our visible and near infrared bands, bands 1 through 6, you can see there's a significant increase. We used to only have band 2, or the visible band, on the previous imager. Another thing I want to point out is not only have we increased the resolution on the visible band, but we've also increased the resolution on the blue visible band, the veggie band, and the snow ice band, which actually increased isn't even really the right word because they didn't exist in the past. So we've got a real significant increase in that. Then if we look at the infrared bands, in the past we had a 3.9, which was our shortwave window. We had 1 water vapor band, and then we had a CO2 band and an IR band. You can see those by the stars on the left. But now instead of 4, we've got 10, and they're all at 2 kilometers versus the 4 kilometers we had before. Significant increase in all aspects from the previous imager. And here's kind of a nice shot. This is one of the first test images that came out in January, as before we even went beta with the data. And you can see just a quick look at all the different bands and all the different information you potentially have. Now this, of course, is zoomed out. You don't get a real good feel for some of the details, but it's in there. So let me quickly move on to the derived products. I know we've got a lot of things to cover today, so I don't want to spend too much time. But you can see all the different derived products that are planned from GOES-16. The ones in red are currently in existence right now. And for the sake of time, I'm just going to talk about one of the specific products, and that's the derived motion winds. I'll be talking about the total precipitable water product during my talk during the NWA conference back in September when we get to Southern California. But for now, we're going to talk about these derived motion winds, or cloud drift winds. These are created from using a sequence of visible and IR spectral bands to track the motion of cloud features and water vapor gradients. The example we're showing here is actually from the Mediasat geostationary imager from the Europeans. The great thing about these winds is they fill huge gaps of area, especially over the oceans, where we don't have any data otherwise. We're not releasing rayobs to get upper air information over the oceans, and this gives us a whole lot of information that we didn't have before. But now with the advances in technology from GOES-16, we're going to greatly add to the amount of derived motion winds that we currently create. So here's an example I took yesterday. If you remember yesterday morning, we had nice little MCS and convective clusters there going on in Illinois, Indiana. And I put on what the legacy GOES derived motion winds at 200 millibars are. You can see there's a few bits of information, especially on the north side of the convection here, another piece here. But if we now go to what we're getting from the new GOES-16, you can see there's an awful lot more information in here in these derived winds. We have so many more data points that can help us out, both from storm scale processes all the way up to synoptic scale processes. It's not perfect though, and so if we look at another image I took from yesterday morning, you notice that pretty much all of the data points are missing some of the information in the anvil section of the convection, and there's the IR to prove it. So Dr. Rabin, who's also on our NWA remote sensing team, is working on a technique based on GOES-14 data, and there's an example of the GOES-14 data, to try to add additional information in that anvil area where our traditional methods have a tough time trying to get some information. So here's an example just of one storm. Just kind of want to show you a little bit of what's going on here. You can see this is a supercell that actually had a EF4 tornado in Katy, Oklahoma last May, and then you can see the overshooting top here marked with the X. So with this optical flow technique that they're experimenting with, you can see that all of a sudden we've got a whole lot more information from the derived winds going on in that anvil area. And if we color code that, you can really see a lot of the difference here in the different speeds going across the flow over the turret from the overshooting top. Gives us a whole lot more information than what we showed are currently getting. Here's an example of the same thing, but now we have instead color-coded speed rather than wind barbs, and you can see the maximum and the downstream effects of the flow around that supercell. So let's do a quick little loop here. You can see this is what it looks like. Again, this is using the super rapid scan from GOES-14. So it does have the 1 minute resolution in terms of temporal resolution, but it only has the 1 kilometer spatial resolution, whereas now we have ½ kilometer. And then here's a loop of what the contour wind speed looks like. And again, you can see this little acceleration in the winds that could help lead us to understand a little bit better what's going on in those supercells. Okay, in summary, we've got GOES-16 is the bomb. It's got some great stuff, and I wanted to leave time to see if there's any questions.
All right, I do not see any questions on the GoToMeeting software. Thank you very much, Frank, for that presentation. That was great. John, do you see anything on Twitter?
It doesn't appear that there are any questions on Twitter either.
All right. Well then, if you do have any questions, feel free again to ask using that hashtag NWAWebWed, or you can ask on the GoToMeeting. But in the meantime, we are going to go ahead and turn it over to Brian.
Thanks, Trish. My name is Brian Motta. I'm with the National Weather Service Learning Office, and I want to just acknowledge some co-authors here, Jeffrey Stano, the GLM Satellite Liaison at Sport, and Steve Goodman, who's the GOES-R Program Chief Scientist. So we're going to try to cover pretty quickly an overview of GLM, introduce what some of the observations look like, and take a look at some pre-operational data from the GLM. So here's the GOES-R spacecraft, now GOES-16, as it's up in orbit. And you can see in the lower left here the actual GLM instrument with a person standing next to it, so you get a sense for the size of it and what it looks like. Some of the specs for the instrument, the big difference here is that we're looking at total lightning activity as opposed to historically we've been dealing with cloud-to-ground lightning strike data. So it's a big change over a large area and at high time frequency in terms of observing lightning activity. A little bit more about the instrument. You can see the inner workings here. There's basically a focal plane array, and it looks sort of like a CCD camera in a lot of respects, a very sensitive one and a large one that looks over the whole hemisphere. So in contrast to radar, the radar coverage for the CONUS looks something like this. One of the utilities of the GLM will be monitoring thunderstorms outside of the CONUS radar coverage area. So overall, this is what the coverage will look like from the GOES East position over 75 west longitude and the GOES West position. So once the two GOES-16 and GOES-17, once both satellites are in orbit and the GLMs are functioning, that's what the total coverage area will look like. So how did we get onto this idea of total lightning? The lightning was first observed by some of the early U-2 aircraft pilots and later by the Apollo and Space Shuttle flights. So here's a sense of what they saw. You know, so you're in space, you're orbiting over space, and you're looking out and you're seeing all these flashes. And so that was the first sort of indication of, hey, this might be something to look at routinely with an instrument. The other bright spots that you see there are essentially the lights of the surface of the Earth. So populated areas with lights showing through the clouds there. Okay, so part of what's going on and what has been going on since launch is some validation studies. I mentioned the ER2, the NASA ER2 plane, and what this figure is showing is an event from the northeast United States, close to the Toronto, Canada lightning mapping array, where these lines on the diagram here are flight tracks where the ER2 flew through this thunderstorm line and behind it. And one of the early findings that the science team has started documenting is the extent of lightning behind the squall line, and that extent is greater than people thought in the past. So that's one of the newer findings. This is a picture of some lightning mapping array data superimposed on a picture of an actual lightning strike in the DC area. And what this is attempting to show is that what we see at the surface, it's really much more complicated once you get up higher in the atmosphere, and you can actually follow some of these lightning sources and strokes to great heights and significant distances away from where lightning may touch ground. And it also, you can see that lightning can touch ground in several different places with one of these flashes. So we're looking at a lot of lightning activity and a lot of lightning energy in the atmosphere, and we'll get into how the instrument tries to separate some of that out in just a second here. So part of the field campaigns for validation are flying these ER2 airplanes through some of these storms, and this is video from the cockpit. If you were the pilot, this is sort of a time lapse of what you would see, and you can see there's a lot of flashing and lightning activity going on that they're flying over and occasionally through. So on the ER2, there's a GLM simulator instrument, so they're getting observations from the storms to compare with what we're seeing from space. So I'll let that complete. One more run through here. All right, so there's three measurements that get made. One is called an event, and that would be similar to these gray boxes, and it's sort of the atomic measurement that gets made. And then the events are grouped into groups, and so we have events and groups, and then the groups are analyzed into what's called a flash, which is the larger quantity of lightning activity. So on a grid, it might look something like this, where there could be 5 lightning event detections, and that gets processed into 2 groups and then 1 flash. So in instances when we have lots of lightning activity, which I'll show you in just a second, these patterns can get pretty complicated. So some initial observations. This imagery is available on the GOES-R website. Let me hit play here. And so this is from a complex of storms that affected Houston earlier this year, back in February. And they had a tornado and some significant flooding associated with this. So you can see the way this has been rendered here, the brightness of the pixels corresponds to the amount of lightning activity, and it's overlaid on a ABI image that Frank mentioned, the ABI instrument. So it's a visible satellite image of the of the event. Some additional observations. Here's an example of something called the GLM group density. So we have the ABI IR at 11.2 micrometers on the left, and the visible on the right, and you can see the group density lightning activity overlaid on the satellite imagery helps to define where in the thunderstorm activity the activity is solid or unavoidable, and where you might be able to, for instance, fly through in an airplane between a break in the line. Here's a little bit closer look. You can see that we're identifying, again, gaps in the storms, looking for the flash activity behind the leading line, and can monitor convection beyond the typical radar range. Here's another look at that loop, showing it in weather in motion, as they say. Here's another example. This is provided by Lockheed Martin, and it's a GLM image from the daytime into the nighttime and then back into the daytime again. So you can see what it looks like during the day, and then obviously at night when it gets dark, we're left with just the lightning detections. And so the way the instrument works is there's a bit of thresholding. We're looking for some of the brightest detections, and that's how we discern where the lightning is. Here's an example of the hemispheric data coverage and some potential operational uses. You can see that we can monitor convection in South America, out over the water, the ITCZ, and then, of course, back in the CONUS over the United States as well. Here's another example with the IR image behind it. And I think you can see for tropical activity in particular, there's a lot of interest in what the total lightning measurements will reveal. So yeah, this is in comparison to the radar coverage. You can see that GLM has uniform sensing across the field of view here. The range rings estimate the 300-kilometer range from the radar sites. So in a loop, this is what it looks like. And for comparison, the NLDN, the National Lightning Detection Network, cloud-to-ground lightning density is in the lower right. So overall, you can see that for flashes, we have about 25. For groups, we have about 300. And for the individual detections, we have about 600. And that's compared with 10 from the NLDN. So the idea is to be able to follow convection more closely and see where the flash rates are increasing or decreasing and how that compares as a consideration with the radar data. Here's another loop of, one more example. For severe weather, I mentioned looking at increasing flash rates. That's one of the predictors for, or one of the factors that forecasters will take into account for looking at severe storms. So let's look a little bit closer at this region. So you can see some strong reflectivity and some flashes from GLM on a flash rate of about 25. So now increasing to 34. And that helps to locate the updraft and the potential for increasing the strength of the thunderstorm. There was a EF1 tornado observed 10 minutes after this, so you can see that that's one of the factors that forecasters will be considering in the future. Example from the Pacific Northwest. not just tornadoes in severe weather country, but lightning and strong storms can happen in other parts of the country. So there are several large aerial extent flashes observed with this case, and you can see that we'll be finding out things that we've never seen before with the GLM. One more example from Minnesota, and you can see this is an RGB satellite image with showing the particle sizes in the clouds and comparing that with where the GLM lightning activity is. So you can see by comparing with the radar image in the upper right, you can see that there's a lot of activity but all across the thunderstorm complex up there in northern Minnesota. And so a summary here showed you some of the first pre-operational demonstration data from GLM. The idea is GLM can detect events, groups, and flashes, and we talked about what those look like. And several applications within this small data set: aviation safety, monitoring convective storms and tropical storms, and severe weather monitoring and prediction. So here's some websites and social media contacts. And with that, I'll toss it back to Trish for any questions.
I don't see any other questions on GoToMeeting, but there is one that came in late, I think intended for Frank, but maybe you can answer it. The question was, how do you request a mesoscale sector? I guess with the ABI.
That's a very good question. Go ahead, Frank.
Yeah, the right now in the Weather Service, it's set up. There's a I didn't want to show it because it's an eye chart, but there's a list of at least 30 different reasons why one might be requested, and they all have a given priority. So in the Weather Service, right now the biggest requester has generally been the Storm Prediction Center, and they try to center it over their areas of slight or enhanced risk. But then there's also been quite a few requests from Western Region forecast offices to help with the fires. So what the offices do is they send in their request with an estimation of where they would like the center point to their regional forecast office representative. Each region has different offices. The one in Eastern Region, for instance, is the Pittsburgh office. Those folks in turn pass it to the senior duty meteorologist up at NCEP, and they make the final call on the request for both the location and the time period. Now there is one of the items in the priority list is for research processes. It's obviously not as high up as operational, but I believe that's still being worked on because we're not, it doesn't really become official until November once it's moved to the east position.
Okay. Well, thank you for answering that. John, did you see anything for Brian or anything that came in for Frank on Twitter?
Nothing on Twitter, just some commentary from Jonathan Bells. He's the only one who's been tweeting about things, but no questions so far.
All right. Well, very good. Well, thank you so much, Brian, for that presentation. We will now pass it over to Sheldon.
Thank you, Trish. Let me Okay, my name is Sheldon Kusselson. I'm retired from NOAA Nestis the last couple of years. Worked in satellite analysis branch for 36 years, and before that I did a stint during the summer of 1975 when the early GOES satellites were launched. So I have pretty much an idea of where we've begun and where we are now, and the reason why I'm still sticking in the satellite game here with GOES-16, even though I'm retired. And one of the things that I've been a big advocate as a satellite guy is inclusion. And in the weather enterprise, we all include, we try to include all types of satellite data so that we can better enhance our forecasts and make better forecasts, more timely decisions on weather watches and warnings. And that's pretty much what I was doing to help National Weather Service folks out there for the 36 years that I worked in the satellite analysis branch. So what I want to try to do is, we've all heard of the forecast funnel. What I try to do is look at the big picture with different types of satellite data first, before I start looking at the closer in geostationary satellite data. So what I want to do is, for today, start with what I look at is a big picture blended TBW for this morning, and showed very high moisture over the Iowa, upper Midwest, lower Great Lakes area, and that's where I'm going to focus my attention for the day, at least for right now, over that area, thinking when I do get to looking at the geostationary satellite data. Okay, so pretty much what we're going to look at is big picture microwave products first, then the big picture GOES-16 for focusing on the most hazardous weather of the day, and then I'll try to give you some idea of mechanics of using GOES-16. This is a lot of data that's come from the past generation to the current generation. It's like a fire hose or an atmospheric river of data that's coming at you, and you've got a whole lot of other things to look at, including radar, actual observations, model data. So you got to have a plan when looking at GOES-16 data to know when to use it, why to use it, and whether to use it in the regular 5-minute mode, whereas now with GOES-13 you only get 15-minute data, or when you have a extreme event or a very, very hazardous weather event in your area, and the mesoscale area is over your area, and you're looking at 1-minute data. So big picture microwave products, I'll just show them briefly because I know this is GOES-16 talk, but I want to emphasize that we're including the microwave products as well to help focus in on the area of concern for the day with the geostationary imagery. The blended total water percent of normal product, and just briefly show the layered precipitable water product, and then next the big picture GOES-16 mid-level water vapor product. So let's first look at the blended total precipitable water products. So like I said, very, very high moisture stretching from Nebraska through the upper Midwest and lower Great Lakes. That kind of catches our eye as an area of big concern. And the percent of normal, which is takes that total precipitable water and compares it with a climatology of precipitable water, is also kind of focusing in on the upper Midwest, lower Great Lakes area, and a little bit of an area that stretches also back to Iowa and eastern Nebraska. The layered and vectored product shows quite a bit of moisture over the lower Great Lakes, both at surface to 850 to 700. But what's interesting is there's a little bit of a connection of moisture from the southwest, eastern Arizona, western New Mexico, on into Colorado, and kind of extends into the Midwest area, which is vecting some mid-level moisture, kind of an enhanced mixed layer that's coming into that area that should focus our attention in that area. And then the big picture GOES-16 water vapor. This is our first chance to look at the GOES-16 data with my talk from a couple hours ago, showing the extensive mid-level moisture that extends from Arizona, Mexico, all the way into the Midwest, which is helping the moisture and convective activity that we were seeing earlier this morning moving across southeast Wisconsin, northeastern Illinois, and toward southwestern and southern Michigan. Okay, some mechanics of using GOES-16 before we actually look at some of the GOES-16 5-minute and 1-minute data. Some of these things I've come up with over my career at looking at 5-minute data, and never really had a chance to look at 1-minute data very much, but I've kind of come up with some ideas on how we could possibly use the 5-minute data, and if you're fortunate to see the 1-minute data, to use it in a particular situation when a mesoscale area is over your area. And I believe there are 2 mesoscale areas, and they will be declared in a particular position based on, I guess, groups of people in the National Weather Service. It could be a local forecast office, maybe, or an SPC type of group, or a WPC type of group. Whether you have flooding concerns, fire concerns, severe weather concerns, I guess it will depend on the highest priority in seeing the 1-minute data. And these are some things that I've kind of come up with, and it's just a guide, and you can kind of look at this after the talk to kind of get a feel for how you'd want to look at this type of data. And you can see with the 5-minute data, you don't want to use a whole lot of images, because 12 images will give you 60 minutes of information, and if it's small scale, slow moving, 1 or 2 cells, that's about all your eye can look at, especially if you're also comparing it with the radar data. A mesoscale, a lot more images, up to 4 hours with the 5-minute data, and in synoptic scale, a nice day over the area. You can look at a longer loop and just kind of track things synoptically as you can. With the 1-minute data, it's a little bit different. You have to remember that geostationary data has been trying to catch up refresh-wise with radar for the life of its for its entire life. Back in the mid-1970s, we started with every 30-minute data. Then the last generation, we started getting 15-minute data, and now regularly 5-minute data. But now we have the capability with at least 2 sectors of 1-minute data. So that's even better than the radar refresh. So we're going to have to come up with ideas to either overlay this 1-minute data, try to do it with radar data, or use it in those very, very hazardous situations. Because with 1-minute data, you get 14 extra pictures in that 15-minute period that we normally with say now with GOES-13, you would only get with 1 picture and then the last picture within the 15-minute period. So so for very small scale, slow moving, 1 or 2 cells, 6 to 12 images at most, up to 12 minutes. If it's a slow-moving system, or something that's maybe changing rapidly but still is slow-moving to produce a severe weather situation, like a situation, tornadoes in Alabama several years ago, that much information for like 6 to 12 images in a 12-minute period would be very helpful for keeping an eye on the various cells that various entities that could result in a tornado or tornadoes during the day. Mesoscale clusters, slow-moving, 2 or 3 cells. Again, you're going to have a hard time really getting an idea with or having your eye check on more than 2 or 3 entities. So 13 to 24 images up to a 24-minute loop. And then just regular mesoscale convective areas, 3+ cells, clusters, groups that are moving. 25 to 96 images would be fine with 1-minute data, and up to a 96-minute loop. Now, let's see whether I can show any current data from today. And I didn't really want to look at the 1-minute data first, but this is a 1-minute sector over the upper Midwest, and as you can see, things are moving slowly in the visible. You can identify thunderstorm here over north central Illinois, pretty much where that moisture was coming in, that enhanced mixed level of moisture that was coming in from the west and the southwest part of the United States over the last 24 hours. And another area of convection over southern Wisconsin, and the main area of convection over southern lower Michigan. And here's the IR for that time right now, ending at 1611Z. Very, very cold top. This is only a 12 frame loop, 12 minutes, but enough to help with your warning and your warning criteria, especially if you want to look at the radar. Another area, a weaker cell over north central Illinois, and then the complex, the convective complex over southwest lower Michigan and northern Indiana. So that's with the 5-minute data. Here's with the 5-minute data, a much longer loop, courtesy of the NASA support people, that showed the convection that we were seeing currently over northern Indiana and southern lower Michigan, where it started originally with a complex over Minnesota, and then fed into an area of convection that was over northern Illinois and southern Wisconsin, and that's the current system that we're watching over the upper Midwest, the 5-minute data. 5-minute data, longer period, more looking at the synoptic, the mesoscale features, whereas the 1-minute data, you're getting into the warning criteria to use that for warning criteria with your radar and everything else that you're looking at. And here is the viz loop with that 5-minute data that started out actually yesterday with the complex that was over the upper plains, and kind of merged in with the convection over southern Wisconsin this morning, and kind of see the overshooting tops real well, at least at earlier in the morning when there was a little bit of shadowing with that. So I've kind of given you a little perspective on, a very little perspective on the how to make this GOES-16 enhance your forecast, and it's an incredible amount of data, and it's an incredible increase in resolution in many of the bands, especially the visible and the infrared and even the water vapor. It's a lot of data, and we have to kind of manage it pretty well to use it at the best it can. And that's all I really have right now.
All right, thank you so much, Sheldon. The graphics are always so fascinating to watch. It's such a neat to have the GOES-16 data in an operational environment. It really is a game changer. It's really very cool. And as Brian said yesterday, you guys you're aiming for cool, right?
And we're aiming for cool.
Aiming for cool. We don't have any other questions that have popped up on GoToMeeting just yet. John, do you see anything? Oh, there's one. Oh, it just says, thank you, Alan. It says very informative, and thanks. It's from the NWA president-elect. John, do you have anything on Twitter?
Nothing on Twitter.
Nothing on Twitter.
Great job, guys. Appreciate it.
All right. Well, Frank, Brian, Sheldon, anybody have any parting thoughts?
Just say that there's more to come, and those of you who are going to be able to attend the NWA annual, we'll get to see a lot of that. There's a GOES-16 workshop during the broadcast session that's planned during the lunchtime on that Sunday, so I certainly encourage all those who will be there in attendance to also attend the workshop. I think that you'll learn a lot and see a lot more new stuff.
All righty. Anything else from Brian or Sheldon?
No, except for being inclusive and trying to use as much data. It's a very, very difficult job now as forecasters with all this information, but the public's expectations are very high for excellent forecasts. So it's a lot different than it was decades ago. There's no sleeping on the job. There's a lot to see and do, and I appreciate what all the National Weather Service people and also the broadcasters of this country are doing and helping to alert the public of serious weather that's to come.
Yeah, Trish, this is Brian. Just encourage people to look at the GOES-R.gov website for continuing updates on the availability of the imagery and data as we go forward and the satellite gets declared operational in the fall.
All righty. Well, we do have one other question that's come in. What is the spatial and temporal resolution of the satellite precipitation estimates?
That I'm not sure, especially since I was associated with satellite-derived precipitation estimates most of my career. When I retired at that time, the rain estimates were to be done every 15 minutes and pretty much on the resolution of the particular satellite. But I think going forward, and you'd have to talk with somebody from Nestis to be official, satellite-derived estimates will be going into the so-called National Weather Service CONUS rainfall estimates that include radar and observations, and especially over the west, where radar coverage is not as good as over the eastern half of the U.S. We would hope that satellite rainfall estimates would be included a lot more in this precipitation product that is being produced now and further improved by the National Weather Service.
Yeah, this is Frank. As I understand it, at least in the way it was originally going to be developed, is that the GOES-R QPE will be, it'll have a 15-minute product will be its highest temporal resolution, and of course it'll have accumulation products that go to several hours and days, and the product spatial is supposed to be about 4 kilometers.
Okay. All right. Well, with that, I guess we will go ahead and close out the webinar. I'd like to thank everybody for attending and especially thank our presenters, Brian and Sheldon and Frank. Thank you all so much for presenting today. Our next webinar will be on Wednesday, August 2nd, and that will be a panel discussion hosted by the NWA Diversity Committee. So we're looking forward to that. And be on the lookout in your email or on social media with the @NWAS account to get the announcement for that. So thank you all so much for attending, and you guys have a great rest of your day.